Today we're going to continue talking about rigid body and we're going to discuss the dynamics of the motion. And the important question to ask is what equations do we need to describe the motion of the rigid body? And here we have a two-dimensional rigid body, and it turned out that the position of every point on this body is uniquely determined by position of two arbitrary points on the body. Let's call these points A and B. Each point has two coordinates in two-dimensional space, and that really means that these four coordinates describe the position and coordinates of any other points on this body. These are four parameters that we need to deal with, but it turned out these four parameters are not independent. And that's because the distance from a point A to point B cannot change in time, and it's fixed. So what we have here, we have four parameters, and we have one constraint. So 4 minus 3 gives us 3 degrees of freedom for the two-dimensional rigid body motion. So we have three independent parameters to describe the motion of a rigid body. In one of the examples, when we have these three parameters, is coordinates of point A. There are two coordinates. And the third parameter is the angle between segment AB and the horizontal line. So we have three parameters. That means that we need three equations to describe those parameters. We can use Newton's second law for the center of mass of the rigid body and the equation for torque and angular momentum. So here we have mass of whole body times acceleration of the center of mass equals to net external force. So what it means is this is the sum of all the external forces applied to this body. By external, what I mean is the force on the body from an external source like earth, walls, etc. It does not include forces between parts of the body like intermolecular forces within the body itself. L here is the angular momentum of this body with respect to some point or axis, and tau net external is the sum of torques of all external forces acting on the body with respect to the same point or axis. Newton's second law is a vector equation, and in two-dimensional space represents two scalar equations. For two-dimensional problems, angular momentum and torque will only have one non-zero component in the direction normal to the plane of motion. So in effect, this equation is one scalar equation. Similar story is with three-dimensional objects like cylinder or sphere when they perform a two-dimensional motion, planar motion. In this case, we normally calculate angular momentum and torque with respect to an axis normal to the plane of motion. Either way, we got three equations for 3 degrees of freedom. In a fully 3D case, we can find position of any point on the body by specifying positions of three fixed points, which do not lie on the same line. Each point has three coordinates in 3D space, total of 9 coordinates. But we also have three constraints: distances between point A and point B and point C, and point A and point C do not change in time. So we have 9 coordinates minus 3 constraints. It means that we have 6 degrees of freedom. And we do have 6 scalar equations because Newton's second law in 3D is 3 equations, and equation for torque is also 3 equations. In any case, Newton's second law for center of mass and angular momentum and torque equation give us everything we need to solve the problem of a rigid body motion. Although I'm assuming that you already know what angular momentum and torque are, I will go through the definitions very quickly. So here we have a system of points, and we also have the point O, which could be one of those points, but it doesn't have to be. It could be somewhere in space. So each of these points is moving some way, so it has a mass, it has velocity, and potentially there's a force, external force applied to these points. So we can number these points, we can call this one, let's say 1, 2, 3, 4, and so on. And let's say we're going to call this point as i's point. So in this case, we can draw a position vector, a vector from point O to this point, and we're going to call this vector Ri. Also, as I mentioned before, this point has to have velocity. It can have external force applied on it. If there's no force, this force is going to be equal to 0. It also has some mass. And what we can do, we can define angular momentum of this particular point with respect to the point O. And that will be a vector product of the position vector and linear momentum of this point, which is mass times velocity. And if we are interested in angular momentum of whole system, we just simply need to add angular momentums for each point. And that's going to give us total angular momentum of the system. In a similar way, we can calculate net torque by getting a vector product of position vector and the external force applied to that point I, and adding for all the points we have. I just want to mention that although I'm using a vector product here, I do not assume that you know what it is. So if you're not familiar with the vector product, that's not a problem. It's not going to affect your understanding of the solution to the problems I'm going to talk about later. Now, going back to our definitions of angular momentum and torque, those are definitions with respect to a point. Now here, I also show you discrete points. In this case, discrete points result in the sum. But sometimes the object does not have discrete points. Sometimes the points are continuous, like in case of a rigid body. And in this case, the sum should be interpreted as an integral. Very often when we consider angular momentum and torque, we're not going to be considering these properties with respect to a point. We're going to be considering them with respect to an axis. So the way you're going to handle these things is, first of all, is to split the vector Ri into two components. One component will be parallel to the axis, and the other is going to be at 90 degrees to the axis, perpendicular to the axis. We're going to do the same thing for velocity and the force. You're going to have a component parallel to the axis and perpendicular to the axis. And then what we're going to do, we're going to calculate angular momentum and torque using the perpendicular components of position vector, velocity, and the external force. But what's interesting, if you do this work, you will find out that angular momentum and these torques are simply the components of this angular momentum and this torque, the components parallel to the axis. When we talk about angular momentum and torque with respect to some axis, really we have only two directions. Like right here, we can see direction up along the axis or down along the axis. And when we have such a binary system, we don't really need to know that angular momentum and torque are vectors. We have only two choices. So in this case, what very often happens, and that's what happens in schools when kids are not introduced to vector products, they're not taught that angular momentum and torque are actually vectors. They're simply told that there's an axis, we want to calculate angular momentum and torque with respect to axis, and then we just need to look whether the object is moving clockwise direction or counterclockwise direction. And that will define whether the angular momentum or torque are positive or negative. And that's sufficient to deal with this problem in that case. When this system of these points rotates as a rigid body around some axis, like the axis right here, in this case, expression for angular momentum becomes simplified, and it's equal to moment of inertia of this system with respect to this axis times angular velocity. Now, moment of inertia is calculated using this formula. Very often we know moment of inertia with respect to some axis of rotation, but that axis of rotation is not always the axis of rotation that we have in a particular case. But there is a very useful formula that relates our axis of rotation to the axis of rotation which goes through the center of mass. The only requirement we need to have here is that this axis of rotation that goes through the center of mass is actually parallel to our axis of the rotation. And if it is, and the distance between those two axes is L, in this case, the moment of inertia with respect to our green axis of the rotation equals to moment of inertia with respect to the center of mass plus mass of whole system, we add all these points together, times the distance between the axes squared. Now let's go back to our equations and let's ask ourselves a question. When are these equations valid? Obviously, we know something about Newton's second law, and we know that Newton's second law is valid for inertial coordinate systems. And if our system is not inertial, in this case, there are extra terms that need to be added to this equation. But in this form, it's only valid for inertial coordinate systems. So it could be normally a stationary coordinate system or coordinate system that moving with constant velocity with respect to stationary coordinate system. But what about the second equation? Equation for torque and angular momentum. Notice we have all these formulas, and in this equation we can use either these two formulas or we can use these two formulas. But in either case, we have R that depends on the point O, this point, or the axis. And also we have velocities here that normally need to be taken with respect to some frame of reference. So the question is, what is a good axis, or what is a good point O, and what is the good frame of reference to calculate velocities? Is it possible to do for any axis, for any O, and can we calculate velocity with respect to any frame of reference? Well, the answer is no. But there are specific frames of reference and specific axes we can choose where the equation written in this form is valid. So let's talk about it. There are three choices. First choice is very simple. Pick up our point O or axis as stationary. The point will not move. In this case, velocities will be with respect to stationary frame of reference, and R obviously going to be with respect to this point O, with respect to this axis. One thing to notice that very often the problems we consider is when the object actually moving. And what you may find, the object is moving away from your axis or point O. In this case, the vector R or R perpendicular is going to grow in time. Now that's okay, that's not a problem. You can do it, and you can use the equation written here. So the second option is to use point O as a center of mass, or have an axis that go through the center of mass. In this case, you have two choices how we can choose the velocity. One way, we can use velocity with respect to center of mass, with respect to this axis, which seems to be like a normal choice. But there's another possibility that you can choose v with respect to stationary frame of reference. That's not a problem either. And there's a third choice, which is the most interesting one. And that's when we choose point O of the axis that has velocity that is parallel to the velocity of the center of mass. But in this case, velocity that we put here, velocities of these points, have to be taken with respect to a stationary frame of reference. One thing to notice that when we take our axis of the point O, position it at center of mass, or this velocity that is parallel to the velocity of center of mass, we need to notice that sometimes, well, center of mass is moving with acceleration. And sometimes our point O in our axis is going to move with acceleration. So technically, when you are in this frame of reference, you are not in the inertial coordinate system. So if we were to calculate Newton's second law in this coordinate system, that would be wrong. But it works perfectly fine for the equation for torques and angular momentums. Now let's get our hands dirty and solve a couple of problems. Here's the first problem. We have a cylinder or a sphere or something like that rolling down the slope. We assume it's rolling down without slipping. So it means the point right here where this object touches the slope has zero velocity. So the first thing we have to do is to draw forces. We have a gravity force that comes out from center of mass, from the point C right here in the middle. We have a friction force that applied to point A at point of touching of the object of the body with the slope. And we have a normal force that's also applied at point A, and it goes at 90 degrees to the slope. Also notice that the angle between the n vector and mg vector is theta, is the same theta as the slope of the incline. The next thing we're going to do, we're going to introduce coordinate system. We have x and y coordinates. We're going to write Newton's second law for this object moving down. That's Newton's second law is applied to the center of mass. Now we're going to write this Newton's second law in the components. Component along the x direction looks like this. The first term, mg sine theta, is the component of a gravity along the x direction, and that component is going against the friction force, which is another direction. And that equals to mass times acceleration of the center of mass. In the y direction, we have two forces. We have normal force one direction and the component of gravity force the other way, and that's going to be mg cosine theta. And since the center of mass, point C, doesn't move up or down along the y direction, that means that acceleration in y direction is zero, and that's why we have zero right here. Now the next thing we're gonna do, since this is 2D problem, or more like we have 3D objects that perform some planar motion, we're gonna write a torque angular momentum relationship with respect to an axis which is at 90 degrees to the plane of motion. And when we do that, we discussed earlier that in this case there are two possibilities for angular momentum and for the torque, is to be towards us or away from us. And to do that, we don't really need to even know that torque and angular momentum are vectors. Instead of that, we can simply say, well, we have angular momentum and torque, which equals to the absolute value of that quantity. And we're going to add plus or minus sign in front of it, depending whether this motion is clockwise or counterclockwise with respect to our axis. One of the motion is going to be positive, the other motion is going to be negative. which one is positive, which one is negative. It's up to us. So let's assume that clockwise motion is positive, counterclockwise motion is negative. When it comes to choosing the axis, we have three choices. One choice is to choose axis as stationary. The other is to choose axis that goes through center of mass. And the third choice is to choose axis that moves with the velocity parallel to the velocity of center of mass. What we're going to do first, we're going to take our axis that goes through the point A and at 90 degrees to the plane of the motion. So this axis will move with the velocity parallel to the velocity of center of mass, because when this point is moving down, and this point A here, just want to point out, is not a point on this object, because the point of the object will move around the object. It's going to rotate around center of mass. Point A we choose here is the point that is always at the bottom of the object and the point of the contact of the object with the slope. And that point is going to travel down the slope, and so does the center of mass. They're going to travel parallel to each other. Now let's calculate torques with respect to point A. Friction force and the normal force, they go through point A, so the torque is 0. The only force that produces non-zero torque with respect to point A, or more like axis A, is the gravity force. And the torque of the gravity force with respect to axis A will be the magnitude of gravity force, which is mg, times the distance from the axis A to the center of mass. And that's the radius, times the sine of the angle between them, which means it's sine theta. Now, the other things we need to figure out is the sign, plus or minus, we need to put in front of this torque. In this case, we choose plus because if you notice, the gravity force is trying to turn this body into clockwise direction with respect to the axis A. And that equals to the derivative of the angular momentum with respect to axis A. Now, when we choose our axis to go parallel with the center of mass, it means that when we calculate angular momentum, we need to use velocities with respect to a stationary frame of reference. And if you remember the video about kinematics, we know that when it comes to point A, the object moves as if it is rotating as a whole with respect to this point A or axis A. And when that happens, we can write angular momentum as moment of inertia times angular velocity. Notice that in this case, we also assuming that angular velocity is positive in a clockwise direction, and angular momentum is also positive in clockwise direction. Now, if you plug this formula into the previous equation, this is what we're going to have. The next thing we want to do, we need to remember again our kinematics. And in kinematics, we related velocity of the center of mass to the angular velocity using this expression. Now, the only thing we need to kind of check to make sure everything works fine is whether we have to have plus sign here or minus sign here. In our case, we need to put plus sign, and that's because positive omega means a clockwise direction with respect to axis A, and that clockwise direction result in a positive velocity of center of mass. So everything works fine right now. But if you were to choose positive direction as counterclockwise direction, we would have had to put minus right here. Now, if you differentiate this equation, on the left we get acceleration of the center of mass, on the right-hand side we get radius times angular acceleration. And now we can replace angular acceleration right here using this formula and get a formula for the acceleration of the center of mass of our body. The last comment I would like to make is that we're using here moment of inertia of this body with respect to the axis A, but typically we are not given that value. Typically we are given value with respect to the center of mass, with respect to this axis. But as I previously mentioned, there's a relationship between moment of inertia with respect to axis A and with respect to axis C. So the only requirements for this formula to work is that the direction of A and C should be the same. So A and C should be parallel to each other. This relationship is known as Steiner's theorem. Now let's consider the same problem, but only with respect to the axis that go through the center of mass, axis C. In this case, when we look at this point CU axis C, we find that both normal force and the gravity go through this point or through this axis. Therefore, the torques of those forces are zero. And the only force that produces non-zero torque is the friction force. The friction force torque will be the magnitude of this force times the distance from axis C to axis A, which is radius, and also times the sine of the angle between them, but the angle between them is 90 degrees, and sine of 90 degrees is 1. And that torque has to be taken as positive sign because this force is rotating our body clockwise direction with respect to the point C. And that equals to the rate of change of the angular momentum with respect to the axis C. Now, the motion with respect to point C is a pure rotation, which could be represented as moment of inertia with respect to the axis C times angular velocity. Like in the previous case, we substitute this value into the previous equation. Notice that the omega dt could be obtained from this equation that will relate the angular acceleration to the regular acceleration of the center of mass. And then we can use the equation right here where we can plug our result and get the formula for friction force. And if we do all these procedures, we find that the friction force is equals to this expression. So now notice what's happening here. When angle theta goes to 0, friction force goes to 0. So what it tells us that if we have a horizontal surface and we have an object moving on a horizontal surface, friction force is going to be 0, which means that this body will be moving in horizontal direction with constant velocity and for as long as you want. So this body is never going to slow down, never going to stop. And that's actually contradict to what we see in real life. When we have a flat surface, we have a cylinder or a sphere that moves on this surface. We find that they can move for a long time, but eventually they're going to stop. What stops this object is actually not the static friction force, not kinetic friction force. What's going to stop them is what's called rolling friction force. And that force is the result of the deformation of the body and the surface itself. But since we're considering now rigid bodies, we ignore those deformations and we assume that there is no rolling friction. But I just want to mention that rolling friction is normally much, much smaller than kinetic friction and much, much smaller than maximum static friction. So what else can we say here? The other thing is that when angle theta is going to go up, friction force that is required to keep this object moving without slipping is going to go up. On the other hand, if you look at this formula, normal force is going to go down. What it means that there is a critical value of the angle theta, and if our angle theta is above that critical value, we find that we will not be able to have this object rolling down the slope without slipping. And in this case, instead of static friction force, we're going to have kinetic friction force. Now let's look at this problem from another angle. It turned out that we can solve this problem or find some answers for this problem using energy considerations. It turned out that in this particular case, we do have a law of conservation of total mechanical energy. Total mechanical energy is the sum of kinetic and potential energy. If we consider a situation when the object was put on the slope with zero velocity and then rolled down the slope without slipping, what we had at the very top was potential energy. Kinetic energy was zero. And when the object gets down, we can say the potential energy at the bottom will be zero, and all we have is kinetic energy. And in this case, the relationship between potential and kinetic energy, relationship between the energy, mechanical energy on the top and on the bottom, would look like this. This is our potential energy, and this is our kinetic energy at the bottom. So H represents the height difference between the center of mass at the top and center of mass at the bottom. Because remember, when we talk about potential energy of the gravity, we talk about the position of the center of mass. Now what we have on the left, we have kinetic energy of the motion. The kinetic energy of the rotating object could be written in the way like this when the object is experiencing pure rotation, no translation. And we know, since this object is moving without slipping, this object is essentially rotating with respect to point A. Kinetic energy of the pure rotation in this case would be written as moment of inertia with respect to the axis A times angular velocity squared over 2. But kinetic energy of the motion could be written in a different way. There's something called Koenig theorem, and Koenig theorem tells us that the kinetic energy of any system could be written as kinetic energy of the center of mass plus kinetic energy of the relative motion with respect to the center of mass. So in our case, it's going to look like this. So the first term is kinetic energy of the center of mass. So we assume that everything all the mass got concentrated at the center of mass and moving with velocity of the center of mass. This term represents the relative motion of this body with respect to the center of mass. And that's going to be, as we know, a pure rotation. And pure rotation is represented as moment of inertia with respect to axis of rotation times omega squared over 2. And this is what we have here. Now, we apply a conservation of mechanical energy here. But you may be asking why. Because the real law relating total mechanical energy, saying that the change in total mechanical energy equals to work of non-conservative or non-potential forces. And typically when we have a friction force is non-potential force. It does negative work, and as the result, it's draining the total mechanical energy. Total mechanical energy normally goes down, but that happens when friction force is a kinetic friction force. When we have a static friction force, what we find that force is applied to the point which is not moving. And therefore, this friction force, or static friction force, does not do any work. And as a result, we can use conservation of total mechanical energy. Now let's look at another problem. Now we have horizontal surface. We have a cylinder or a sphere that moves along this surface. And let's assume at the first moment, whole body is moving, every point of the body is moving with this velocity v naught. So this object at the first moment is moving without rotation. And the body was put on a surface that has friction. And that means that the point right here, at the bottom, that touches the surface, moving with velocity v naught, while the surface itself does not move at all. Therefore, this point is moving with slipping. And therefore, we do not have static friction, but we have kinetic friction. And as I mentioned before, for that problem, we cannot use conservation of total mechanical energy. But we still can write Newton's second law, we still can apply torque equation, and that's what we're going to do. Let's first put forces. We have gravity, we have normal force, and we have a friction force. Now here I draw normal force and mg with some horizontal shift, but that's just to show the forces itself, just for picture. In reality, they both should lay on the top of each other. Now gravity is applied to the center of mass at point C, and friction force and normal force apply at point A. We can write Newton's second law. We can introduce coordinate system, and we can write Newton's second law in x direction and y direction. Since friction force is kinetic friction force, we know the formula for kinetic friction as a function of the normal force. It's coefficient of kinetic friction times normal force. Since normal force in our case from this equation is mg, that's the expression for friction force, or for magnitude of the friction force. We can plug this value into this equation and get this expression for the acceleration of the center of mass. So this formula, this derivative of the velocity of the center of mass, is acceleration of the center of mass, and that equals to minus coefficient of kinetic friction times g. Notice that acceleration is constant in our case, and since acceleration is constant, that means that velocity of the center of mass is a linear function of time. And that's the formula for this. Notice that when t equals to 0, Vc should be equal to V naught, this V naught as it should be. The next thing we want to do, we want to write a torque equation. Again, we need to specify positive and negative directions. So again, we're going to say that positive direction is clockwise, negative direction is counterclockwise. The axis for torque equation which we can use are stationary axis, axis that goes through center of mass, and the axis that moves parallel to the center of mass. In this case, we're going to use the axis that goes through center of mass. In this case, normal force and mg are going to have zero torque. The friction force is going to have a positive torque equals Fr times radius. And that equals to the rate of change of angular momentum with respect to the point C. Now, when it comes to calculating angular momentum with respect to center of mass, we can either use velocities with respect to the stationary axis or velocities with respect to center of mass. And if we do this, we find that this body is rotating with respect to the center of mass. So we can write the center of mass as moment of inertia with respect to the center of mass times omega. Plug this equation in the first equation, we get this relationship, we've done it before, and rearrange the terms, we find an equation for the angular acceleration. Angular velocity is constant, therefore angular velocity is a linear function of time. It's going to be written this way. Notice I already took into account that when t equals to 0, omega should be 0. At the first moment, the object is not rotating. But now notice something interesting. Velocity of center of mass is going down because there is a friction force applied to this object. That makes sense. But omega, angular velocity, is increasing. So while the center of mass is slowing down, the object actually starts rotating faster and faster. And the question is, how long is it going to continue? These formulas are derived in one specific case. They are obtained under specific assumptions. An assumption that we use is this. We assume our friction force is kinetic friction force. As long as there is a slipping, yes, friction force will be kinetic friction force, and we can use these formulas. But is it going to continue all the time? Is it going to continue till infinity? That's what we need to figure out. So let's write the velocity of this object at the bottom point, at point A. So the velocity of point A with respect to the ground equals to the velocity of center of mass plus velocity of point A relative to the center of mass. Notice that there's a minus sign right here. And that's because when this object is rotating clockwise in a positive direction, when omega is positive, the relative velocity of point A with respect to point C is actually negative. Now we're gonna use formula for VC from here and formula for omega from here, and we're gonna put them in this equation. If you do, this is the relationship you're gonna have. You notice what happened? VA is actually starting at V0 at t equals to 0, as it should, and then slowly going down, 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 down in a linear fashion with time, and eventually there's going to be a point when VA going to become 0, and at that point our kinetic friction is going to become static friction. And we know in this case static friction is equals to 0, and this object is going to continue moving forward forever with constant velocity. So we can do some kind of analysis. We can find, for example, a time when this is going to happen. So the time t star, when velocity of point A is going to become 0, and we're going to have a no slipping condition. That corresponds to t equals to this value. And also we can calculate the velocity of the center of mass from that point on. And that's it for today.